Hi everyone. In this video I'm going to talk about a theory that we will use in conjunction with the Lewis structures that now you have learned to draw to predict three-dimensional structures of molecules. And the theory itself is called valence shell electron pair repulsion theory, usually just shortened as VSEPR, which is the first letters of each of these words. So it's normally just called VSEPR theory. So the question is, first, why do we need this theory? What is the advantage of knowing the three-dimensional structure that we didn't get just by looking at the Lewis structure, which is a two-dimensional or a planar structure? Because if you hopefully you realize at this point that all these Lewis structure you're drawing, basically they're drawings on paper, so they're planar, they're just on paper. But molecules, of course, are three-dimensional structures, three-dimensional objects like other objects you see around you. So the question is, what is the advantage of getting a three-dimensional structure versus a two-dimensional structure? Well, it turns out that a lot of physical and chemical properties of a molecule, particularly chemical properties as far as whether it will undergo reactions, what kind of molecules it would bond with, and so on, come not only from the atomic composition of the molecule, in other words, what kind of atoms make up the molecule, but also in how the molecule looks like in three dimension. Okay, in other words, what we call the 3D structure, three-dimensional structure, or molecular geometry, all of these terms mean the same thing, which is how the molecule looks like in three dimension, plays a very important part in how the molecule works. A very classic case of this is illustrated by the structure of the DNA, which of course most of you know is the material, the genetic material in your cell that's being transmitted, that's being copied, and then distributed from mother to daughter cell. Okay, so way before the discovery of the three-dimensional structure, in other words, before people knew what DNA looked like, it's already quite known, quite widely known because of a lot of biochemical experiments and the like, that DNA is the genetic material that basically contains the information that makes us what we are. And then people also knew at the time that this particular information, this genetic information, is somehow copied from the mother to the daughter cell, okay, during cell division. But it's not clear exactly how this happens. Now, the structure of the DNA, which was published in 1953, provided a fairly clear picture of how DNA does this. In other words, how it's copied from one generation of cell to the next. And this is shown here as, again, most of you probably have seen before. The DNA has this, what we call the double helix structure. In other words, you have one strand of DNA going this way, and the other strand of DNA going this way. And that's what you see in your cell. They're all wound up together. But that's what the DNA will look like if you just remove everything else around it. It will have this double helical structure, and there's all these small atoms that come out of it, each what we call bases and so on. There's no need to understand that part of it for our purpose here, but the structure makes it very clear that when DNA is being duplicated, basically what happens is there are processes that takes apart this double helix. So in other words, it kind of separates the two helices from each other. And then there are certain enzymes and whatnot, which people have worked out now, that basically copied the instruction from one helix and generates this new helix here, which is the green one. And then there's another set of enzymes that does the same thing for the other helix. And as a result, originally you have two strands of DNA, two helices. Now, as a result of this copying, now you have four helices, right? And of course, this eventually split apart, and this goes to two different cells, the daughter cell. So from one cell you split into two, and the DNA is copied accordingly. And the structure really provides that information that lets us understand how this process works. So that's the importance of knowing three-dimensional structure. Okay, now let's get back to VSEPR theory because that's what we're going to be talking about here. The VSEPR theory itself, it's useful not so much for prediction of, really big molecules like DNA, but it's really useful for predicting smaller ions or molecules, whether they're inorganic or organic compounds, that you can draw lowest structures of. So as long as you can draw lowest structures of the molecule, within reason, the VSEPR theory can be used to predict their three-dimensional structure. And like I said here, it's actually going to be very useful in organic chemistry because you'll actually be using it to some extent to predict or to kind of at least visualize in your head what the molecule would look like. Now, I want to emphasize here again something I mentioned earlier, which is that Lewis structures are two-dimensional structures. So when you draw all of these Lewis structures that you've been drawing, they're just two-dimensional. They're planar structure. They're something you draw on paper or on the board. They don't have three-dimensionality or depth to them. But these VSEPR structures would have three-dimensionality to them. Okay, so what in essence is VSEPR theory? Well, basically it just says that we assume that electron pairs surrounding an atom, okay, in its valence shell, because the valence electrons are the ones used for bonding and interacting with other atoms. These electron pairs, because they all have negative charges, will repel each other to the maximum extent possible. In other words, they want to get away from each other as far away as possible because that's what they are. They're both negatives, all these electron pairs. They're not going to want to be close to each other at all, okay? As a result of this repulsion, electron pair repulsion, the atom that contains this electron pair is forced to adopt specific electron geometries relative to the other atoms in the molecule, okay? Because the electrons want to get, as far away as possible from each other, the atom has to then adopt a particular geometry that would allow that, repulsion to happen, okay? Those are what we call VSEPR geometries, VSEPR electron geometries. Now, as a result of these electron geometries, whether the electron you have are bonding pairs or lone pairs, you're going to get specific molecular geometries, which are the three-dimensional structures that is a result of the specific electron geometry that you have from VSEPR. Okay, so there are two terms you need to keep in mind here: electron geometry and molecular geometry. Electron geometry doesn't depend on whether it's bonding or lone pair. You just kind of combine all of those together and count just how many electron pairs you have. Molecular geometry depends on whether you have bonding or lone pair. And I'll kind of clarify this in a couple of tables later on. Okay, so again, here's the idea of VSEPR. Let's say a central atom in this case has 3 electron pairs, okay? And the 3 electron pairs happen to be bonding pairs in this case because it's bonded to these 3 other atoms. It doesn't really matter in this case, but what matters here is that the assumption is that these 3 pairs are going to want to stay as far away from each other as possible, and there's only one structure, one geometry that allows that to happen, and that's when this angle between this pair with the central atom with that pair is 120 degrees. That will be the furthest away they can get away from each other. I'm going to show you another example, which is methane, CH4. Okay, so here's methane. If you were to draw the Lewis structure, it will look something like this, right? Now, what you want to see, of course, is that here you have an angle if you draw the Lewis structure, and this is the furthest you can get away from each other in terms of electron pairs. So the methane molecules has 4 electron pairs, 1, 2, 3, and 4, and the furthest they can get away from each other is a 90-degree angle based on the Lewis structure. But, of course, like I said earlier, Lewis structure only considers two-dimensional structure, okay? But if we were to build a model in 3-dimension, we'll see that actually you can get even further from each other, these 3 electron pairs, if you adopt a structure of a tetrahedron, okay? So here's it's kind of a building, a model of this will be shown in a second here in this video. In fact, this person will bring it in. So here's the model of methane. And as you can see here, I want to kind of see how he turned this around, but this angle This is your central atom carbon. This is hydrogen. This is hydrogen. You can see that this angle is not 90 degrees, right? 90 degrees would have been like this right here, okay? But this is a little bit bigger than 90 degrees. In fact, the angle itself is 109.5 degrees. That's what we've observed experimentally. And if you build a model, that's basically what allows you to get as far away from the other electron as possible, these two electron pairs, okay? So again, you can see it when it's being turned around, maybe a better idea of what that structure looks like. That's what we call a tetrahedral structure, okay, of a molecule, because that allows the four electron pairs to get as far away as possible. So he's rotating it so for you to be able to see it clearly, okay? And we'll have other models as well as I'm playing in the next video that you'll be able to kind of observe this a little bit better. Okay, so going back here, I want to kind of end this video now and continue in the next video to talk about VSEPR theory and then start applying it to certain examples, talk about the actual electron geometries, the molecular geometries, and how we actually use VSEPR theory in practice. But remember, the CH4 example is quite important because, again, you expect a 90-degree angle if you just look at the Lewis structure, but the actual structure has a hydrogen-carbon-hydrogen angle of 109.5 degrees, okay? So, and the reason is because in 3D, electron pairs can actually be separated even further than what you expect from the Lewis structure itself, okay? All right.